Alright, so we're still on chapter 3. This is the second lecture. We are simply working some problems. This is the one we worked the last time. Let's step things up a bit, make it more complicated. Let me read it first. To what volume should we dilute 50 milliliters of a 5.00 molar potassium iodide solution so that 25 milliliters of the diluted solution contain 3.05 grams of potassium iodide? So you want to be careful here. It's not a straightforward dilution, but you are going to use the M1V1 equals M2V2 equation, which you don't have to, because you're always, if you're calculating a molarity or a volume, you just need to know the number of moles and the volume. But this one comes in very handy in this particular case. So we do know the original molarity and the original volume. We're told we're going to use 50 milliliters and a 5.00 molar potassium iodide solution. But we don't know the volume. That's what we're asking for. What's the final volume going to be? But we don't know the final molarity either. So this is a little tricky. See, this is not the final volume. We're asked for that. But we are told that that 25 milliliters of that diluted solution should have 3.05 grams of potassium iodide in it. And so that's the key. So we're going to need those 3.05 grams of potassium iodide and figure out the number of moles, and then we can divide it by the volume to get the molarity. And so that's how we get to the final molarity, and then we can solve for the volume. Alright, so that's of course potassium iodide times 1 mole of potassium iodide divided by 166.0 grams of potassium iodide. That is the molar mass, of course. That gives me 0.0184 moles of Ki. So that's what we want to have in the 25 milliliters. So if we then simply say 0.0184 moles of Ki, and we divide that by the volume, of course, in liters, 0.025 liters, that gives us a molarity of 0.735 m. So that is actually M2. Now we can take the dilution formula and solve for V2. So V2 is simply equal M1V1 over M2, which is, and we can keep this in milliliters. Alright, so we can say 5.00 m times 50.0 milliliters divided by the 0.735 m, and that gives me a final volume of 340 milliliters, right? So this we don't need to convert to liters, because this is moles per liter, and so this is also moles per liter, and so they simply cancel, and our answer is in milliliters. Since I don't ask specifically for you to solve for the volume in liters, you can leave it like that. Okay. This is the problem all worked out in detail. And the next problem is again a step up. What volume in a soft drink that is 10.5% sucrose by mass contains 78.5 grams of sucrose? And the density of the solution is 1.04 grams. So we're given a percent and we're given a mass. Okay, so the way I would tackle that is by first applying the percent. So what we're looking for is a percent is a part divided by total times 100. That's the formula for percent. And so we are given the part, right, 78.5 grams. And we're given the percentage, but we're asked for the total, right? So what volume of the soft drink do we need? And that's the total. So we want to solve for total. So you multiply by total and you divide by percent, and then the total equals the part divided by percent times 100. So let's do that. We know the part, 78.5 grams, and we know the percent, it's 10.5, and I'm going to lump the 100 into there. Instead of dividing by 10.5 and multiplying by 100, I'm just going to write 0.105. That's the percent fraction, and I get for that, I'll look that up real quick, I get 747.6 grams. Now, all I have to do is, in order to get to the volume, because it's asking for volume, is apply the density to that. So, times 1 milliliter divided by 1.04 grams, and that gives me a solution of 718.86 milliliters solution. But of course we only have 3 significant figures, 1, 2, 3, and this would be 719 milliliters. Alright, so since it's not asking for molarity or moles, we don't actually need this. Alright, so here's the problem all worked out. Okay, moving on to colligative properties, which are solution properties. For example, the boiling point and the freezing point, which are altered when you have different things dissolved in a solution. And so the example that you may be familiar with is that when you boil pasta, sometimes people add salt. What that does, it'll cook the pasta faster because it will increase the boiling point. So having stuff in solutions will alter the boiling point. It will increase it. It's called boiling point elevation. We also put salt on the roads in the winter so that the snow will melt at a lower temperature. So a solution of sodium chloride in the salt will actually lower the freezing point, and so the snow can melt at a lower temperature. Okay, and so it does that depending on how much is in a solution and what is in a solution. If you look at some data here for boiling point, and one thing that is the same here is all of those solutions are 1 kilogram of water, and then we add something to it. All right, and it's also in, I said that already, it's all in water. And so if we just have pure water, it boils at 100 degrees and it freezes at 0. And if we put 1 mole of sucrose to that, the boiling point will go up by 0.512 degrees. If the freezing point will go down by 1.86 degrees. And so if you put 1 mole of ethanol in there, it'll do the same thing. So it doesn't matter whether it's sucrose or ethanol. But if you put 1 mole of sodium chloride in there, you're actually doubling the effect, right? So this will go up by a degree and it'll go down. It will go down by twice as much. So there's a factor of 2 here. And that's because of the Van Hoff factor. That's because of how many particles are actually dissolved. It doesn't matter what it is, whether it's sodium chloride, sucrose, or magnesium sulfate. It matters how many particles result from the dissolving. And so we know that both sucrose and ethanol are nonpolar covalent compounds. They're not electrolytes, so they don't break into ions. They simply dissolve because they have OH groups. But they don't break apart, so you get 1 particle per mole, and so that is a Van Hoff factor of 1. But sodium chloride and potassium bromide, there break into two particles. Sodium chloride will break into sodium and chloride ions. That's two particles, and that's why we see doubling of that effect. And same with potassium bromide, that's two particles. And so we call that the Van Hoff factor. Now, the Van Hoff factor is actually not a little bit different than 2, 3, 4, right? So if you have magnesium sulfate, you have two particles. If you have magnesium chloride, you get magnesium ions and two chloride ions. So that's actually 3 particles. But your Van Hoff factor is going to be close to 2.7. Now, in all of these problems, if I don't tell you what the Van Hoff factor is, you will assume a whole number, the expected Van Hoff factor. If I give you a Van Hoff factor, that refers to, that is the number of particles, which is I. Right? So we use this formula here. The change, delta always implies change in something. So here's the change in temperature, BP, standing for boiling point, and here change in temperature, FP, freezing point, and they depends, the constant for that, which is KBP or KF, depends on what it is that your solvent is. And so if your solvent is water, guess what? Your freezing point depression constant is going to be 1.86 degrees per molal. Okay, so it's exactly going to be that, because we took 1 mole, and the boiling point elevation is going to be 0.512 degrees per molal. Those are the constants for water, and I'll always provide those to you. And so we multiply by the molality, that's little m, so it's number of moles per kilogram of solvent, and then times this Van Hoff factor I, which for non-electrolytes, meaning polar covalent compounds that don't break into ions, is always going to be 1. So ethanol and sucrose is going to be 1. Okay, so let's take a look at some examples here, right? So what is the boiling point of a solution made from 0.87 grams of magnesium sulfate and 15 milliliters of water? Okay, so magnesium sulfate is soluble and will produce 2 particles, magnesium and sulfate, right? That's something that I will not tell you. That's something that you need to know. This is a soluble ionic compound containing of magnesium and sulfate ions. That will tell you the Van Hoff factor. Okay? Now we need to molality. We're given I don't provide you here with the KB, but it's 0.512 degrees per molal. That's that for water. It's not shown here, but in order to get molarity, I need to take the number of moles divided by the kilograms of solution. And so I'm given grams, and so I take that and convert it to moles. That's where that 0.0723 comes from. Then the kilograms of solvent, it's 15 milliliters of water. So that's where 1 kilogram, I'm just converting that to kilograms here. 15 grams and kilograms is 0.15. That gives you the molality, and of course don't forget that the Van Hoff factor is 2. So now that we can put in for that, and here's your freezing point depression constant, or that's boiling point, sorry. That's the constant for the boiling point, times the molality gives you 0.494 degrees. That is delta, that's the change in, so you still need to add that to the 100 degrees, which is the normal boiling point of water. Okay, let's take a break and then come back and work a few more of those in the 3rd lecture.